okay, or you identify things that are polar. Okay, so to introduce you to polarity, a very easy way to think about it, you have to know about this thing called electronegativity. And this is my rendition of a periodic chart. So this is our periodic chart. So the deal is here, in terms of electronegativity, some atoms have a real strong propensity to grab and to keep electrons. So think about them as being strong in a tug of war. They're very strong. In the tug of war for electrons, they're going to get most of the electrons. They're going to share unequally. Yep, they're going to get most of the rope. And then you've got your wimps on the other side. And the wimps, well, they're strong enough to hang on to the rope, but they're not going to have much rope. So they can't hang on to electrons very well. There's a general trend that you need to know. This is important. Hint, hint. Okay. So the strongest, well, first of all, these you can kind of forget. Why? Because we're talking about sharing electrons, and we know noble gases don't form molecules. So if they don't form molecules, then, and you're going to learn why in a little bit, but if they don't form molecules, then they're not sharing molecules. Okay. So what I want to do is point out the most electronegative element there is fluorine, right there, top right. That's it. Nothing is more electronegative than fluorine. Nothing can grab electrons stronger than chlorine. So, and we're talking about electronegativity is that thing that we talked about, which I'm going to abbreviate EN, electronegativity. Yes? And so for electronegativity, fluorine is numero uno. Your wimp, your biggest wimp is right down here at francium. That's the weakest one. It's the least electronegative. So the general trend in electronegativity is this. I would know this if I were you. Electronegativity increases from bottom to top, and electronegativity increases from left to right, ignoring, of course, the noble gases. So if fluorine bonds to potassium, right? We got potassium fluoride. Then potassium is not going to get very much electrons, and fluorine is going to have most of the electron. Electrons are going to hang around fluorine most of the time. And the further apart these get on the periodic chart, the more lopsided it is. So if oxygen and fluorine form a compound, which they can, okay, it's still going to be lopsided. So oxygen and fluorine actually do form a compound. And guess what? They're lopsided. And sometimes we draw a little arrow to say. That's like a little plus sign. That means across this bond, since fluorine is more electronegative, the electrons are going to be hanging around fluorine more than they do oxygen. And likewise, on this side. So what we have is, each of these bonds is polar, to where this one is oxygen is kind of sort of positive, and fluorine is kind of sort of negative, right? It's polar. So, but they're not real ions. So here's how you might see it in a textbook. They show a lowercase delta with a positive. So what this means is, across this bond, they're sharing it, but we show unequal sharing, just like we would if it's positive or minus. But we can't just put plus or minus there. Why not? Because these aren't ions. But they're kind of sort of getting there. So we call it, so the delta means partial. So that means oxygen is partially charged positive compared to fluorine, and fluorine has a delta negative charge. So you can kind of see the magnet. There's a positive end and negative end. And each bond is like that. Every bond, every two atoms has a polarity. Okay. And one of them's going to be kind of sort of negative, and one of them's going to be kind of sort of positive. Why? Because they're going to share unequally. Unless, of course, it's the same atom. Let's look at fluorine, one of your 7 diatomics. Fluorine is what? F2. Remember that? F2. Well, which one of these is going to pull harder? This fluorine or this? And the answer is, well, neither. They're exactly the same. Right. They're exactly the same. And so this material would be said to be what? Non-polar. Yes, it's a non-polar molecule. How come? Because they share electrons, but they share them equally. Okay? So it's not really lopsided. So how do you tell if a bond's lopsided? You look at the difference in electronegativity. Okay. Now later I'll show you how to determine if the molecule as a whole. So this is a tripwire you need to know. There's 2 types of polarity. There's polarity across each individual bond. In this case, I need to show that I can show you that there's actually 2. I need to also draw S minus here. Okay. So this bond is, I have a polarity here across this bond. And I've drawn a little arrow to show you that I know which way the electrons are headed. They're hanging out more. And I have an electronegativity for this bond. Okay. When I showed you this polarity earlier, this polarity here, that polarity is referring to the polarity of the molecule as a whole. This bond has a polarity, that bond has a polarity. But the entire molecule itself has a polarity. And that's what we're talking about earlier with the Lewis dot structure cascade that I showed you. And the overall polarity is just going to be the shape of, determined by the shape of those, the sum of all of the bonds. Okay, so let's continue on. I know this is a lot of stuff, but hey, I'm going to present it, then you're going to read it in the textbook, and you're going to work problems, and it's going to all make sense. I can tell you this part, if you're just going to listen to my lecture and think you've got it, you're going to be sad. It's going to be a sad day, because that's just, chemistry normally doesn't work out that way. Okay, so let's show you some examples. HF. So this is covalent, it's sharing. So there's 2 ways. Now you've already seen there's 2 ways I can represent the unequal. How do you know, first of all, how do you know they're unequal sharing? Well, I do. And how do I know that the arrow points that way? Well, you look back at your periodic chart. And you see that F is here and H is here. And since electronegativity increased this, you know the electronegativity of fluorine is greater than the electronegativity of hydrogen. So you know you have unequal sharing. Which way is the electron's going to head toward mostly? Fluorine. Why? Because it's furthest to the right. You know your rule. Okay, so with that rule in hand, let's do this. So you know from your periodic chart, fluorine is more electronegative than hydrogen. So what does that mean? You could represent that a couple of different ways. You could put the delta minus there and the delta plus there. And I do that sometimes. But the one I really like to do is just draw the arrow right across the bond where the arrow points to the most negative part. And that little cross thing, it kind of looks like a plus sign. And that means that end of the molecule is plus. Okay? If you're in physics class or you're mechanically inclined, you might think of this as just being a magnet, because these are bonded together to make a single structure, an HF molecule. So you may think about this as being a magnet to where this end of the magnet is negative and this end is positive. All 4 of these representations are used to represent, to designate the polarity of a molecule. Okay, so let me contrast now and show you how electronegativity is useful. Now, I showed you the general trend. Electronegativity increases from bottom to top and left to right. Well, they're also given numbers, just so you know. Each things are assigned. Each atom has a certain electronegative value. And so I'm just going to tell you what a couple of them are. I'll give them to you so I can do some math, so I can quantify this. This is qualitative, right? You can see the direction. Quantity, I want to put a number with it. Okay, so you don't have to know this. If you need to know this for the test, I will tell you. But the most electronegative fluorine has a value of 4. That's the scale. The scale goes 0 to 4. 4 being the most electronegative, 0 or something near 0 being the least electronegative. So what determines how big this bond is, this arrow is? What determines how unequal the sharing is just how big this difference is. Now remember I told you F2 wasn't polar at all because there's no difference. Well, you can see that. 4 minus 4 is 0. So again, I see the difference in electronegativity is 0. It's not a polar bond. It's nonpolar. Okay, well, let's look at HF, the second thing we went over. This molecule, fluorine, has a value of 4. And just so you know, hydrogen has a value of 2.1. So what's the difference? 1.9. So I know it's going to be polar. Why? It's pretty strongly polar. If you do enough of these, you'll say, man, 1.9 is really getting up there. So that's a very polar bond. Well, I can actually quantify it now. So I know very much most of the electronegative charge is going to be here, and just a little bit of positive is going to be on the H. Are there some things that are slightly polar? Yep. Remember I showed you OF2 a minute ago? Well, let's look at those differences. Fluorine is still 4. And something I would tell you if you need to know in a test would be oxygen's 3.5. Well, what's that difference? 4 minus 3.5 is, is only 0.5. So it's polar, but it's not very polar. So you can see we can actually put orders of magnitude. Something that's not non-polar, something that's slightly polar, or something that's very polar. So what you will be expected to know is the trend in the table. What you won't be expected to know are these numbers. Well, who cares? Well, what does that have to do with anything with the chemistry? Well, let me ask you this just based on that. Let's say we have a material and we make crystals out of it. We make a solid material. How do you think they're going to stack? Are they going to stack like A? Or are they going to stack like B? And the answer is they're going to stack like B. Why? Because notice, you've got a positive to a positive. Mother Nature doesn't like that, right? Opposites attract. And what do you have at this end? You've got negatives near negatives. Now you can see they are going to stack this way. See why Mother Nature would like that. Okay, so this looks good. A negative end is connected to a positive end, and that positive is to a negative, and that negative is to a positive. So going left to right, I predict they're probably going to stack that way. I think that's how it's going to go. A head to tail to head to tail to head to tail stacking. That looks good. That looks really good. What doesn't look good is my up and down stacking. Because what? I've got positive next to positive and negatives next to negatives. Hopefully you can see that. See? So along this way, I don't like that. Was there a way I could fix both of them? Yeah. So look at the bottom. Now what if the molecules stack like this? I've got a positive connected to a negative. Let me go back to red. I've got a positive to a negative, and then this negative to a positive and positive to negative. So my opposite track, I like that. But now look what I have up and down. The negative end of this one's near the positive end of that one, and the positive end of this one's sticking to the negative end of that one. So I like that too. So you could use some simple logic to actually predict how molecules are going to stack when they become a solid. That's an area called crystallography. You don't have to know that, but crystallographers who do this stuff for a living and look at how solids are shaped, right? Is that important? I don't know. Anybody ever watched that Forged in Steel or whatever where they're making the knives? Well, guess what makes a good knife or not? Depending on whether the molecules stick together good. Turns whether it's brittle, whether it's durable, whether the blade's going to stay sharp. Well, all of that relates to what's called crystallography, the way things pack. And what I want you to understand here is just understanding this little bitty bit of information that you know in intro chem, you can actually start understanding how that works. Okay. So that's the concept of polarity. I want to take a side and just do some true confessions here. When we say this, the formula of sodium chloride is NaCl, it's really not. Because in one salt crystal, you've got thousands of NAs and thousands of Cls. So what happens is you see the crystal because you have multiple millions and millions of plus minus. See, that's the chloride and that's the sodium. Well, that sodium connects to another chloride, which connects to a sodium, which connects to a chloride, which then goes deep into the page. And that negative is next to a positive. And so this lattice, this huge structure keeps growing until it's so big you see it as a salt crystal. Well, the molecular weight of that crystal is trillions and trillions and trillions. So what you'll see sometimes is formula unit weight. And the formula unit weight means what's the weight of 1 unit of of sodium chloride. I just wanted you to know that because if you see formula unit. So formula unit is to this structure what empirical formula was to molecular formula. This is like the empirical formula, okay? And this whole thing, depending on how big it is, would be like the molecular formula. Okay, when you deal with ionic materials, they don't call them empirical formula and molecular formula. What they call them is the formula unit. Okay, just want you to know it, because when you're not dealing with covalent materials but ionic, they use a little different nomenclature. But between us, somebody asked me what the formula of sodium chloride is. I'm telling them sodium chloride. And they just have to know I mean the formula unit. Okay, so there's a difference. All right, here's where the concept question comes in. And this is kind of an important slide here because I'm going to pull together a lot of what you've learned this entire semester. It's taken all semester to get you here. So let's kind of go over this, and I'm going to overlay what I just taught you with what you already knew earlier and kind of bring it all together. Everything from covalent to ionic compounds and how strong those interactions are. So this is a really good summary slide of a number of concepts that the book and a bunch of these problems try to get over. If you understand the big picture, if you understand from a 30,000 foot view or 10,000 foot view what the forest looks like, it's a lot easier when you're down in it to navigate your way around. So here we go. Here's your 10,000 foot view. What I'm going to show you is what I call the polarity spectrum. And the first thing you need to know is something you already know. There's two types of compounds. In this world, there's what? There's covalent and there's ionic. That's it. There's two types of reactions, redox reactions and ionic reactions. And there's two types of compounds, covalent compounds and ionic compounds. Fine. So what we studied the first 2.5 months of this class was almost exclusively, with very few exceptions until we got to redox. The only thing we dealt with was ionic materials because they were easy to understand. Opposites attract, make them charge neutral, and you got it. Okay. Then we got into redox reactions. Okay, then we got into redox reactions, which were a little bit hairier, and now we're going into the molecules that make up redox reactions or covalent compounds. Okay, but the punchline is there's only two species that we're interested in. Now, I just told you covalent compounds that are formed by sharing electrons. There's two flavors. There's nonpolar molecules that are not lopsided in terms of electron sharing, and molecules that are polar, those that share electrons kind of in a lopsided. Furthermore, we learned some things can be just a little bit polar, or things can be really polar. So we have nonpolar, a little bit polar, a lot polar. So we kind of sort of have a spectrum there, and that's what I'm showing you with here. So we have covalent, nonpolar, slightly polar, and really polar. So let's imagine this like a rubber band, something that's nonpolar. So let's look at this bond. If they're equally sharing, then there's not much stretch on the rubber band. Things are fine. But how about if somebody starts tugging harder? Now we've got unequal sharing here. A little bit. The difference in electronegativity is not so much between H and I, but it's a little bit. So we're stretching the rubber band a little bit more. HBr, you'll see that they're further apart on the periodic chart. Now the rubber band, the covalent bond in this case, is getting stretched harder. It's more polar. More of the electrons are here and less of it's there. It's getting more and more bipolar. Then you get HCl. Now you're getting really up there. Difference in electronegativity is 1.5. The rubber band is really stretched. This is really negative and that's really positive. Then you get to HF. Hydrogen fluoride, the one we looked at earlier. This is really lopsided. Fluorine is a whole lot more electronegative than H. The difference in electronegativity is 1.9. The rubber band is just about to break. And then you get to sodium fluoride. It's an ionic compound. It crosses the barrier here. Why? Because the rubber band snaps. At this point, it was so lopsided that the electrons just completely fell away from the sodium. It couldn't hang on anymore. So it became positive charge. Why? It couldn't hang on to its electron it was sharing. It lost it to the fluoride. Fluoride's now a negative charge. Why? Because it not only has all of its electrons, its original electrons, but it now has sodium's electron too. And so now we move into a whole nother class of chemistry, the ionic chemistry. Now, let me continue. So you can also have ionic materials that are weakly ionic or strongly ionic. And this is the entire polarity spectrum. Covalent nonpolar, covalent slightly polar, covalent real polar, weakly ionic, and strongly ionic. As an aside, let's review ionic compounds just for 1 second here, and let me review something. Sodium chloride has a positive 1 and negative 1. The sodium has a positive 1, and the chloride has a negative 1. So it's slightly ionic, I will say, or weakly ionic. So let me show you a rule of thumb somebody figured out. And this is a really good rule of thumb. That's a positive 1, that's a negative 1. What's 1 times 1? Forget about the charge. What's 1 times 1? It's 1. Okay, fine. Now let's look at another compound, calcium chloride. You know if you combine calcium and chloride and make a charge-neutral compound, it's CaCl2. What's the charge on the calcium? +2. What's the charge on the chloride? -1. What's 2 times 1? 2. That's interesting. So somebody figured out that, hey, if you just multiply these charges, the bigger that charge is, the more tightly they're going to hang on together. Well, no kidding. Really strong magnets are going to stick together more strongly than really weak magnets. Okay, so let's look at calcium oxide. We've seen that one before. Calcium's +2, oxygen's -2. So what is that value going to be? 2 times 2 is 4. So calcium oxide is really strongly held together. Oh, guess what? Remember when things precipitated? Yeah, most things that precipitated had a high number here. Okay, right? Why? Because they're holding together so tightly, they don't dissolve in the water. And so hopefully now you're even starting to understand now why some things dissolve in water and why some things don't. The story is, of course, a little more complicated than that, but that's the basic gist of it. Now let's look at something that is really held together tightly. Calcium has a +2 and a phosphate ion. We know phosphate is -3. 2 times 3 is 6. So calcium phosphate very well might be a candidate to precipitate in water. It might be really hard to dissolve that in water. Why? Because it holds together so tightly. Okay, so ladies and gentlemen, there you have everything we've taught you for the year. 2 types of materials. Each of them has either nonpolar or polar, has weak and strong, or weak and strong versions, and there it is. And it explains everything from the way something is structured, the way its crystal structure looks, everything to whether it's likely to dissolve in water or not. That's where this is going. So again, when we talk about this polarity, I want to link this to you though. Remember, that's where we're going in the lab. When I talk about this polarity, that's what that means. When I say something is polar, what that tells you is it's a yes-no answer as to whether is it here, is it polar, or is it non-polar. And this is what you're going to get out of the lab. Okay, so this is the theory behind what you're going to learn to do in the lab. Okay.